Hello everyone, welcome back. Let's talk about another hard problem on Leetcode today. AllOne data structure Leetcode 432. In this problem, we have to design the data structure to store the strings count with the ability to return the strings with minimum and maximum counts. So we should implement the class called O1. We are calling the constructor will initialize the object of the data structure. Increment method with the key increments the count of the string key by 1. If the key does not exist in the data structure, we should insert it with count 1. Similarly, calling the dec method should decrement the count of the key by 1. If the count of the key is 0 after the decrement, we should remove it from the data structure. It is guaranteed that key exists in the data structure before decrement. getMaxKey should return one of the keys with the maximum count. If no such key exists, then we should return empty string. Similarly, for getMinKeys, we should return one of the keys with the minimum count. If no such element exists, we should again return an empty string. And note that each function must run in average time complexity of O1. What this means is that in general, there may be a scenario where the time complexity may not be O1, but still the overall performance should not grow with the size of the data structure. Then in example 1, first we initialize AllOne class, then we increment hello's frequency by 1, then we again increment the frequency, so now the frequency becomes 2. Then it says get maximum key, so there is only one key in the data structure, so because of that we will return hello as an output. Then it again says get min key, so again there is only one key with frequency 2, so we will return hello again. Now we increment the frequency of lead. So now data structure has two keys in it, with hello having frequency 2 and lead having frequency 1. Then we get the maximum key that returns hello. Then we get the minimum key and then we return lead. So this was the whole example. Now in terms of solution, when we look at these frequencies, what data structure comes to the mind? And the answer is hashmap, right? Because then this is very similar to the frequency map, where strings are keys and values are frequencies. So here we can see that hello has frequency 2 and lead has frequency 1. So this will be actually very useful when we are actually incrementing or decrementing the count or frequency of these words. So the time complexity there will be O of 1. But the challenge is for getMaxKey and getMinKey, we want the keys based on the values. For example, the maximum frequency here was 2. So we want the corresponding string. So because of this, the time complexity becomes O of n, even though the increment and decrement operations had time complexity of O of 1. So how should we overcome this problem? One of the naive ways can be that we actually sort the map based on the values, but that will again require O of n log n, which is even worse than O of n. Another approach can be that we can use some balanced binary search tree like AVL tree or red-black tree, because then the order remains sorted. But then again, when we have to do rotation or when we have to insert the values, that will take O of log n time, which is better than O of n and O of n log n, but still not good because we want O of 1. Now note that when we are incrementing and decrementing the count of the keys by 1, then the relative order of the frequency changes just by 1. For example, word hello had a frequency 1 and we increment the count, then its frequency will become 2. So just changes by 1. Similarly, if we decrement, its frequency will become 0. So how about we actually use a data structure such that when we are inserting the values or updating the values, we can sequentially reach out to the next and previous element and keep the keys sorted based on these frequencies, similar to what we do in the insertion sort. And then the data structure choice can be array, singly linked list or doubly linked list. But array has a fixed sizing and also deletion will be O of an operation. And for singly linked list, we cannot go to the previous element at all. So when we decrement the frequency, we cannot reach out to the previous element. But the data structure which will be super efficient in this case will be doubly linked list, because suppose we have to increment the count, then we have to just move the key from one node to another one, because the frequency changes by positive 1 only. Similarly, if we are decrementing, then we have to just move the key to the previous node, or in the worst case, we have to delete the node if the frequency becomes 0. And the time complexity for both the operations will be O of 1. So we can use the combination of hashmap and doubly linked list to store the keys and corresponding frequencies in the sorted order, similar to what we do in the LRU cache. So in the map, we can store the keys and the value will be corresponding doubly linked list node. And in that node, we can actually store the frequency and set of keys which actually have the same frequency. And in the doubly linked list, we will actually store the order from lowest frequency node to the highest frequency node. And the map will be containing the key and the corresponding node value. So whenever we want to increment the count, we will get the key, get its current node. For example, this was a node. Now because we are incrementing the frequency, we have to transfer the key to the node with one frequency higher. If it doesn't exist, we have to insert the node in the doubly linked list. And after the transfer, update the value for the key pointing to this new doubly linked list node. Similarly, when we are decrementing the count, we have to transfer the node from current node to the previous node. And in the worst case, if the frequency becomes 0, we may have to also delete this key. And we can treat our doubly linked list as double-ended queue, where we can use two dummy pointers, head and tail, where head will have a quick access to the maximum frequency and tail sentinel node will have a quick access to the minimum frequency. The head pointer points to front of the queue and the tail pointer points to the rear of the queue. So this setup simplifies operations at the boundaries, such as inserting a new node at the front or rear of the list. So whenever we are inserting the value, we will try to insert it at the tail, because then we know that the frequency is 1. And as the frequency increases, the node moves towards head. And if the frequency reduces, then node moves towards tail. So now let's see this in action. Let's take this example and suppose these are the instructions. So first we initialize our AllOne data structure with an empty hash map and an empty doubly linked list with head and tail pointer. So note that these are like dummy pointers, they don't hold any values and they will also not be part of our answer, but they are just here to make our operations easy. Then we get the string A and we increment its count, but A is not in the map and also frequency 1 does not exist in the doubly linked list. So we will create a new node with frequency 1 and insert it at the tail node. Note that I have marked this node as N1 and the frequency of letter A here is 1. Now the linked list has tail node N1 and head node. And in the map now we will have the character A and corresponding frequency node N1. And now we increment the frequency for word B and we can see that B is not in the map. But when we traverse the linked list from say tail pointer, we can see that there already exists a node with frequency 1. So what we will do is we will actually add B to the key set of node N1s with frequency 1 and also add B to the map. So for key B, we will be pointing to node N1. Then we will continue. We get a new instruction. We increment B's frequency by 1. So we can see that B already exists in the map and the corresponding value is node N1, which has the frequency 1. So we check if there exists a node with frequency 2 in the doubly linked list. And that we can do just by going to the next node of node N1. And we can see that there exists no node with frequency 2. So we will create a new node N2 and add B to its keys with frequency 2 and also update the map. So now our key will be B and the value will be N2. Now we perform the operation of incrementing count for C. We can see that C is not in the map, so its frequency will be 1. And then we see if there exists a node with frequency 1 in the doubly linked list, say by traversing from tail pointer, and we can see that there exists node N1. So we will add C to the keys of node N1 and update the map with key being the C and value being the node N1. And then we again perform the operation of incrementing the count for C. So now C's frequency will become 2 and there exists N2 already in the doubly linked list with frequency 2. So we will add C to the keys of N2 and update the map. So now for C being the key, value will be N2. Then we again get the instruction for incrementing the count for C. We see that C is already present in the map and corresponding node is N2 with frequency 2. So now the frequency for C will be 3. So we hop to the next node of N2 and see if node with frequency 3 exists, and the answer is no. So we will create a new node N3 and update the map. And now for key being C, value will be N3. Now we get the operation for decrementing count for B. So now B's frequency will become 1. And because B is the only key for frequency 2, we will delete N2 and move B to frequency 1, which is the previous node N1, and update the map. So now A and B both point to N1, but C points to N3. Then we again get AllOne.decrement B. So now B's frequency will become 0. So we will delete B from N1 as well as from the map. And we can see that there exists still key A for N1. So we will not delete this node. And now in the end, our map has key value pairs as A to N1 and C to N3. And at any point, if we want the maximum, then we can just go to the previous pointer of the head pointer. For example, for this doubly linked list state, we can just go to the previous pointer of the head node, and there we can see that the frequency is 2, and then we can return any of the keys here, so either B or C, as the keys with maximum frequency. Similarly, if at any point we have to get the minimum, we can just go to the next pointer of the tail pointer. Here, for example, that would have been N1 with key being A. So that's how the whole logic will work. Now let's jump into the code part. We start by creating a map and head and tail pointers. So we create a map where key is an input string and node is a doubly linked list node with the frequency. So let's also define the node. So it will contain previous and next pointer for the doubly linked list. Also, it will contain the frequency, and it will also contain the set of keys which have the same frequency, and a constructor where we can pass the key and the corresponding frequency, and we will add this key to the set of keys. Let's also create default constructor for the dummy nodes, and we can pass the values with key being empty and frequency being 0. I think we are good for now. So now let's create the dummy pointers for head and tail. Now let's connect them in the constructor. So what we can do is we can just say tail dot next as head, because these are the only nodes present in the start of the linked list, and head dot previous as tail. Now comes the first method where we have to increment the frequency of the key. So either the map can contain the key or not contain it. So let's first handle the case where map does not contain the key. So first we check if our list is empty, that is tail.next is equal to head, or node with frequency 1 doesn't exist in the map. The frequency should be 1 because the key doesn't exist in the map, so the initial frequency will be 1 here, and we can easily check if the frequency of the node is 1 by going to the next pointer of the tail node, because the minimum frequency in the list can be 1, and if it is not present after the tail node, that means it doesn't exist in the list. So if the list is empty or node with frequency 1 does not exist in the map, we should create a new node with current key and value 1. And now we will insert this new node after the tail pointer and add the key and corresponding new node to the map as well. So now let's define our insert method, which actually inserts the node after the tail pointer. So this method takes a node that needs to be inserted and inserts it after the current or this pointer. Node.previous will be this because we are calling it on the tail pointer. So the previous pointer of the node will be pointing to the tail, and node.next will be equal to tail.next now. So we will just do this dot next, and node.previous will be tail, right? So tail.next will be equal to the current node, and node.next.previous will be now pointing to the current node because we have to break the previous connection of the next node with the tail node. So now we have inserted the node. But if there exists a node with frequency 1 in the doubly linked list, that means we can add this key to the key set of this node and add key and corresponding doubly linked list node to the map. So now we have handled the cases when the key is missing from the map. But if the key is already present in the map, in this case we have to just increment the frequency. So we will get the current node from the map, and first we check if the next node is pointing to the head, that is we are at the end of the list, or the frequency is not equal to current frequency plus 1, then we should actually create a new node with current key and frequency equal to current frequency plus 1. And then we should add the new node after the current node and add the current key and this newly created node to the map. Otherwise, if the next frequency node exists, then our case again becomes simple. We will add current key to the next node's key set and update the current key's value in the map to next node. And once we are done with it, we have to remove the key from the current node's keys. Also, if there exists no key with the current frequency, then we should get rid of this node as well. Now let's define this remove method. So when we are removing the node from the list, that means we have to disconnect it from the list. So we can just get the previous node and its next will be equal to current node's next. We have to do the same thing for the next node as well. So we just get the next node's previous value to point to this node's previous value. And now we are done with our increment method. We will do the same thing for our decrement method. For the decrement method, it is guaranteed that key exists in the data structure before we do the decrement. So we don't have to check if the key is present in the map or not. So we will get current node from the map and check if current frequency is 1. then that means we have to remove this node. So we will first remove it from the map. Then in any case, we have to remove this key from the keys of the current node. And if there exists no key with current frequency, then we should delete this node as well. Now, if current frequency is not equal to 1, in that case, we will just decrement the frequency by 1 and go to the previous node of the current node. So first, let's get the previous node. Now, first we check if the previous node is tail, that is we are at the start of the list, or previous node's frequency is not equal to current frequency minus 1. Then we should add the new node to the doubly linked list before the current node with the current key and frequency equal to current frequency minus 1, and also add this newly created node to the map for the current key. Otherwise, we will add the current key to the previous node's key set and update the map for the current key with value being the previous node. And I think we are also done with the decrement method. Now getMaxKey and getMinKey, if our algorithm so far was correct, should not be very hard. For getMaxKey, we will check if our list is not empty, that is tail.next is not equal to head. Then we should access the node just before the head sentinel to get the key with the highest frequency and return any of the value from the key set using the iterator. Otherwise, we will return an empty string. Similarly, for getMinKey method, we will again check if the list is not empty. Then we should access the node just after the tail sentinel to get the key with the lowest frequency. Otherwise, we will return an empty string. And I think that's it. Now let's run this code. Now let's submit this code. Awesome. In terms of time complexity, as the data structure's name suggests, all the methods take O of 1 time. And in terms of space complexity, it will be O of n, where n is the number of keys in the data structure. So I hope this video was useful to you. If it was, please like, share and subscribe. The code link is in the description below. Thanks for watching. See you next time.